do some introduction of who we are. So we are based at the University of Oulu in the north of Finland, very high in the Scandinavia. And essentially, we are part of the 6G flagship program, which is the first program looking at 6G wireless systems. And our group, essentially, which is ICON for intelligent connectivity, is looking at, of course, what intelligent communication means and control. And of course, AGI is one of this. Our group is fairly large. I may just bird's eye view again here. So Anis is here, Abdul Mumin is here. So I'm just highlighting the Libyans in the group. There's also Nadia coming very soon. So very excited to have as many Libyans as possible. All right, so now to the talk. So of course, to get to AGI, we need to understand a little bit where we have been working on. So typically, intelligence has been associated with centralized machine learning, right? This is where you have all the training and inference algorithm happening. So you may have a bunch of sensors, devices. It could be, a sensor, a VR, a drone, whatever. And typically what you do, you transmit this raw and privacy sensitive data to the cloud, and then the cloud just trains your model, right? So obviously this is terrible in terms of privacy, incurs very high latency if you are working in wireless communication, and it's terrible in terms of bandwidth efficiency. So 2017, surprisingly, Google came up with this very basic idea, in fact, looking at it now, of course, with insight, of now, instead of communicating raw data, what you would do, you have, again, a bunch of distributed devices, and they would communicate what we call models, right? So this model essentially could be just, tantamount to running few steps of your, say, stochastic gradient descent or other optimization algorithm, and just communicate these updates over the air. And then the server now will just aggregate this model and then send them back, broadcast them back to these devices. And this process, iterates until some sort of convergence is achieved. So very basic idea, but essentially it's bandwidth efficient because you're no longer communicating raw data, which could be highly dimensional, right? Especially in the uplink where you may be limited, but you also still use the cloud in a different way. So now the training does not happen at the server. You just average these models, and of course you can do other type of operation beyond just averaging, right? And again, as I said, this is privacy preserving. Now, if you want to get rid of Google, you can do the same thing now at the level of, say, a random topology. So these are, device to devices, or mesh topologies. Say in a factory, you have your robotic arms, and again, they have to train this model, this global model, in a totally collaborative manner without sharing their raw data. Okay, so this is called swarm AI or fully distributed AI, right? Now we'll be basically focusing this in this talk due to the lack of time. So I guess everybody knows what federated learning is, but essentially there are two types of, say, federated learning. There is a cross silo, right? So this is maybe hospitals or banks or, let's say, factories or companies trying to train their models. So typically here again, you have lower number of, say, clients or entities, right, which participate in the model training. Contrast that with the cross-device federated learning, which is maybe more relevant to, let's say, wireless communication, so sensors and so on and so forth, where, of course, now you have a much larger number of sensors or devices, and typically you only have a fraction of these devices available to join this training process, unlike, let's say, in a hospital or in a factory where these clients are always available. Okay? So a lot of challenges, of course, in federated learning, and of course this has been trending since 2017 or maybe even before. So there are a lot of challenges ranging from communication efficiency, of course, fast convergence, test accuracy. This is a little bit what has been the focus since the beginning, and now we understand that you need to look at also other metrics than just maximizing test accuracy. Energy efficiency, a big deal, right? Nowadays with sustainability and climate change. Obviously, privacy and generalization, right? This is essentially, of course, what machine learning is all about. Now, in terms of resource constraints, you have, of course, the constraints in terms of wireless networking, bandwidth, but also memory, compute, storage. So these are all under the umbrella of resource constraints. And again, how do you train federated learning or other variants, of course, of AGI under these constraints? Federated learning has been already used in a number of real-world applications. So, for example, this is maybe a couple of distributed factories, maybe Libya, maybe across the world, and then you want to really maximize or improve the robotic maintenance across all these factories. Of course, this may be competing factories. You could, of course, just use perhaps vanilla federated learning, or any more sophisticated approach of federated learning. This is, of course, happening in the context of one of our EU projects. You can also do it at the level of wireless communication. You may have, again, base stations from different operators, and they want to maybe collaboratively train a model to, for instance, estimate the average interference or average traffic load in their network, again, without sharing sensitive information. This is also possible using federated learning. Currently, we have this EU project where, again, now federated learning is used for example, for navigation, right? You have distributed maybe autonomous driving or here tractors, and you want them to train a model so as to do, for example, image segmentation, right? You want them to, for instance, identify that there is, for example, an obstacle on the field, and you want them to learn that as fast as possible. Now, obviously, because you have different fields of view for every tractor. So again, FL appears to be an interesting candidate. Okay, and of course you can do it at the level of healthcare, agriculture, retail. I mean, it's kind of ubiquitous nowadays. Yeah. Now, more let's say coming back to what we do in the group. So this is again a really high-level view. So again, I told you that we are trying to look at the intersection of both machine learning on one hand and wireless communication. This is essentially where we think the kind of the impact is larger, instead of just looking at machine learning completely abstracting communication. So again, you have a lot of constraints, small data paradigm, device constraints, data is non-AID, right? And as I said already, the channel network interference constraints we are used to. So how do you really look at this co-design between machine learning and wireless communication, right? By looking at fundamental questions. So how do you train a model, right, in a communication efficient, energy efficient, robust manner? Assuming you have a pre-trained model, how do you now do, collaborative inference, right, over distributed nodes? And of course, you can push this, maybe Vanit has already mentioned this, so at the level of reinforcement learning or control, right? So control theory and reinforcement learning are typically, kind of sister, let's say, areas. Okay, so for this talk, and I guess I have to maybe rush a bit, so we will just overview a number of techniques. So I call them zoo of techniques because there are really many. So one will be the model parameter exchange. This is where federated learning sits, right? You also have model output exchange or federated distillation, which is an idea we developed a few years ago with the collaborators from Yonsei. And of course, you could do meta learning. I won't have time to dwell into this. I'm just going to cover very fast how we applied federated learning and federated distillation in some works. So it was actually the first work about the application of federated learning in ultra reliable vehicular communication. So here we are in 5G, not 6G. Here the problem was as follows, right? You have a number of vehicles and you want them to essentially reliably communicate traffic safety messages, right? And the latency constraints. So you can, of course, pose this as an optimization problem. And typically what you would realize is essentially that this latency constraint here, which is captured here, you either have to learn it, right, individually, meaning by every device or vehicle, or collaboratively using, for example, federated learning. So that's essentially what we looked at. We tried to essentially learn the tail distribution of this network-wide latency from data, right? So again, you can see here that you can just, this becomes your device, this becomes your server, which could be a roadside unit, and then you just average now the models of this blue part of the distribution. Again, remember, we are in this extreme event scenario of ultra reliable communication. And here we already have some inductive bias in the sense that we know this follows a generalized Pareto distribution, which means I can just estimate this distribution from data. So you can pose your maximum likelihood and estimate the shape and scale of this distribution, again, using federated learning or maybe other techniques you may have in mind. Now, this was, of course, 2018 or 2019, or with the conference version. So what we did, we looked at the benefits of federated learning compared to a centralized setting. So a centralized setting, you communicate all the samples that the vehicle is observing to the server, which is, trains a model for you, versus applying federated learning. And we compare this in terms of reliability, right? That's what you see here in orange, total number of vehicles and exchange data or payload. So the good news, essentially here, we get a free meal type of result in the sense that we achieve the same reliability as the centralized approach, but we get much more gains, you can say, in terms of communication efficiency. For the simple reason is that we communicate just these parameters instead of transmitting the traffic safety message. Bear in mind that this gain could be much, much larger if we were talking about, let's say, communicating or dynamic maps, right? In the case of dynamic maps or navigation, the gains will be much more pronounced. Maybe somebody can look at this setting. Moving on now, so this is the other type of algorithm, very nice idea, inspired from the teacher-student analogy problems. To know what you have now, again, a bunch of devices here, again, could be anything you have in mind. Now, instead of communicating these model parameters, which can be actually kind of large, right, 100, a million of parameters or even more, right, communicating this over the air isn't going to be possible. So what you do instead, essentially, you communicate what we call logits, right, or model outputs, right? This could correspond essentially to taking just the richer signal, right? We refer to logit or output distribution, then average this essentially, again, using some sort of averaging, and this will be kind of the teacher knowledge, which we try now to distill, right? So now you have the student device, which is trying to learn, but with an additive kind of feedback, you can say, from the teacher, right? And this is exactly what you can now write mathematically. If you're familiar with how the weight updates of let's say, stochastic gradient descent, typically you have your weight updates, your learning rate, first order loss, gradient of your loss function, right? But here we add this kind of structured regularizer, which is essentially capturing the difference between the prediction of the student on its own, based on its own local data, but also the prediction acquired from the teacher, right? So again, if this difference is small, it means that there's no need to add this regularizer. And of course, if it's larger, then you take into account in terms of learning. Very fast here, the gains that you can obtain with such techniques. So here we compare the federated learning and federated distillation in terms of communication costs and test accuracy. So you can see that we have massive gains in terms of communication costs. Of course, again, communicating just a few bits, you can say, right, as opposed to a very large number of parameters. There's a small hit in performance that you can see here, but in follow-up works, we managed actually to bridge this gap by combining the benefits of federated learning in a downlink and federated distillation in the uplink, which is where your uplink limited. Okay. Another very important topic, of course, I told you, test accuracy maximization is not really the only metric we need to look into. So green AI or energy efficient AI is very important topic. So we have tried to look at this from a more empirical perspective. So we just try to compare essentially, who is more energy efficient, centralized learning, federated learning, or completely distributed learning. So we run really a bunch of simulations here, making some assumptions on the type of costs you may have in terms of communication, computing, and also carbon footprint. We cannot, although this was empirical, there were a very nice insight in the sense that now, if your data is IID, right, in fact, it turns out that federated learning is green or energy efficient. This is again for, let's say, 90% target loss. Now, however, so again, more energy efficient than centralized learning. Now, if your data is highly skewed or non-IID, we completely see a difference in terms of inflection point, where, for example, here in the case of IID, you need 43 rounds to converge. It goes up to 62. Why? It's very simple. In fact, or kind of there's an intuition behind it. Is essentially in the, let's say, the skew distribution, the devices living at the tail, on the tail of the distribution, have to constantly, communicate, or more frequently communicate than the devices living in this, the average or the middle of mode of the distribution, right? They have to constantly remind the server that, of course, they have their own data that will be reflected in the global model, right? That's essentially, in a nutshell, the reason for such result, which tells you, of course, that sometimes having a global model, it can hurt the performance of local device. This is maybe why you need maybe to look at by meta learning. Maybe you need to look at clustering. There are a lot of other techniques that can be investigated. Now, moving a bit also to another technique which is very popular also, split learning. So now, as the name suggests, now what you can do, you can take a large network, neural network, and you can really split it in terms of multiple segments. So now what you talk about is pushing forward this forward tensor to the server, which continues training the or computing rather for you, and then you can maybe send back this computing or forward tensor back to the device, which can either continue training, right? Because maybe you have privacy issues here. This could be, for example, this could be hospitals, right? So the labels of the patients are sitting here, right, at the hospital, not in this third party, which is just used to kind of offload the computing. So this is very interesting because it solves really real world problems and also has a better, let's say, privacy guarantees, we can say, than federated learning. Federated learning, although it claims to be privacy preserving, there have been some reconstruction attacks. As far as I know, maybe this has not happened in speed learning. Maybe it has, I'm not sure. But in terms of applications in the wireless domain, this is very interesting because we can look at settings where you can do joint inference of the sensors or the device or the server, right? This is sometimes also referred to maybe, semantic communication for some people, but this is essentially a split learning idea, right? So how many layers do you need to have at the sensor? How many layers do you have to have that server? Take into account, again, storage, memory, compute, bandwidth constraints. So there's a nice optimization here to be done. But for us, what we did, we tried to apply this in a nice setting, a 5G use case, or maybe the 6G use case, where we wanted to predict in advance, right, whether there will be a blockage from a base station to a user before it happens. So you can do this using different modalities, maybe using radio signals or using cameras or LiDARs or other kind of sensors. So what we did a multimodal sensing and fusion in this sense. So we could train a model now which combines, in some sense, both modalities. So if this is the modality of the camera, right? So you need, again, now to know how much you compress this information, which you feed, in fact, as an input to your LSCM, in this case, for the receive power prediction, right? And then you can complement some data from the receive power if you have it. Otherwise, there's no need for that. So that's essentially what we looked at, very practical setting. And these have some results which kind of compare the multimodal sensing and fusion, but also when you have, let's say, if you're constrained, let's say in privacy, you could do a 1-bit feedback, say, if you compress a lot the images taken by the camera because you don't want to show maybe there is a child or a person, right? You can see here that combining just this 40 by 40, which corresponds to this filtering of the CNN, you can get better performance than using RF signals only. Now, if you don't have concerns with privacy, you can see that there's a kind of an interesting point here, 4x4, which allows you to trade off a bit, communication bandwidth, but also test accuracy, right? That's essentially what we looked at. What's next? Many things. So of course, depending whether you wear the theoretical hat or the practical hat, federated learning today is all over the place. But again, maybe it's good to now realize what's missing. So one of the things, of course, so meta learning is already happening today. But I think causality or causal representation learning is something very important. We don't see much of it today because essentially we're still learning statistical models. We know that the human brains doesn't operate that way, right? There are other type of high-level reasoning, cognition mode that we need to embed, maybe even in model-based RL, maybe in other aspects. That's essentially where research is going today. Energy aspect, already mentioned it today, right? So maybe trading off accuracy, energy, robustness, generalization, right? But now a bit just to finish on this, what we are currently looking at and very excited about, which I think will not only help communication folks, but also machine learning folks, is this one, right? Semantic communication, which may mean different things to different people, but here really the idea is we want to reverse flip the paradigm by, instead of communicating more and more data, or communicating even the model parameters, we want to actually reverse that. Can we transmit less data and leverage knowledge, right, to achieve more, meaning by solving as many tasks as possible, by generalizing, right? And for this, I mean, the reason is because we want to unlock new use cases which go beyond just learning statistical patterns from data, which we are doing today using federated learning or others, right? Two, of course, if 6G, which is our focus, is about really human-machine collaboration, intent, ChatGPT-3, type of language now between the human communicating with the robots, then we need to look at the human psychology. So there is this nice system 1, system 2 idea we're trying to explore. System 1 is essentially what we use today in all the machine learning works because it's just learning statistical models again, right? Interpolation, we don't extrapolate. So system 2 is the one that we should look at. So there are a lot of people in machine learning community already looking at that. System 2 allows you to plan, slowly deal with exceptions, reason, right? So today, the new kid on the block, we can say, is reasoning. Reasoning by abstraction, reasoning causally, and so on and so forth, right? So again, semantic communication will be the technology that enables at least us to go beyond the current, let's say, system one technique. So I don't know how much you know about semantic communication. I just have one slide on this. So this all goes back to Shannon, of course, 1948, 1949 paper, which defines 3 levels of communication. So level A is essentially what we have been exploring since 2G, right? You have a sender, has a message X, communicate to the receiver using source channel coding. The receiver has to really reconstruct X. So X equals X hat to some extent, right? And the reason for that is because back in the days, in the 40s, semantics was not interesting, not relevant. Computational aspects, of course, were there. But in fact, channel removed completely meaning, it removed structure, removed memory. And information here was a scalar, right? It's really related to the, entropy minimization, you can say, right? Shannonian type of information. It turns out, in fact, that there are 2 other levels of communication which will definitely impact not only communication, as I said, but also machine learning, because they are related to meaning. How do you extract meaning from data, number one? And how do you communicate it to a receiver? And then the receiver actually doesn't need to decode the entire packet. It has to infer the intent of the sender so as to solve the task. So what we are doing now, we are bringing back whatever Shannon removed by leveraging structure, leveraging abstraction, memory, other stuff other kind of ingredients which are very important. And now the goal is not to do reconstruction, right? Sender to receiver, but now really to, again, infer this intent, right, via interaction, because here again, you have a kind of a protocol emerging between the sender and the receiver, right? And how do you use now, not statistical inference anymore, but logical inference, reasoning, and so on and so forth. And now information, maybe some people know this, information means different things to different people, but here we are talking about shapes of information. What kind of topology the information lives in? Can we characterize that space? Can we, do some sort of algebraic operation on that space? That's essentially what the human brain does. That's the system 2 modes of cognition that we're trying to now kind of incorporate in communication, but also machine learning. So again, this is what we really mean by semantics. And my final slide is, with that, we can really look at very challenging use cases which cannot be solved with just federated learning. You want to talk about what kind of emergent protocol will be arising via interaction between robots and factory, right? These guys will not use human language, obviously. So what kind of signaling are they going to use? Also, how can a human teach a concept to a robot? How can the robot just observe, from pixel information and infer the intent of what the order, the prompt of the human, right? This could be solved as maybe formulated as an inverse reinforcement learning problem, and so on and so forth. There's a lot of stuff here. This was a 2-year-old slide before even ChatGPT-3 came, but you understand that, of course, even the fundamentals of ChatGPT-3 based on transformer architecture are definitely intersecting, related to this system 2 modes of cognition, semantic communication, so on and so forth. So that's essentially what I would even advise students, because of course doing a PhD today on FL is a bit risky. There's a lot of works. So why not jump on this new topics, which again will help both communities, not only communication, but also control theory, by the way, but and machine learning. And with that, yeah, thank you very much.